Welcome to the pre-lab discussion for experiment 6. In this week's experiment, we're going to carry out a substitution reaction and isolate the products. We're going to be using two nucleophiles, which will potentially react with our substrate through a substitution reaction. And our goal is going to be to determine whether one of the nucleophiles preferentially reacted with the substrate. In order to do so, we're going to use gas chromatography mass spectrometry to analyze the product or products produced. Let's take a look at the specific substrate we'll be using, which is 1-hexanol, shown here. We're going to treat 1-hexanol with two nucleophiles, ammonium chloride as the source of chloride ion, and ammonium bromide as the source of bromide ion. We're going to carry this out using water as a polar protic solvent, and we're going to add sulfuric acid to the mixture. When we consider the potential mechanisms for substitution reactions, you've learned about SN1 and SN2. In order to decide which is likely to occur, we have to holistically look at these conditions. Let's start with the substrate, which is primary. Given that we have a primary substrate with no resonance stabilization possible, it's unlikely that we're going to form a primary carbocation. This leads us into an SN2 pathway instead of an SN1 pathway. We know that the requirement for an SN2 reaction is to have a good leaving group. However, when we look at the substrate we've been given, OH- is not usually thought of as a great leaving group. That's where the sulfuric acid is going to come into play for us. The sulfuric acid is going to act to protonate this oxygen of the alcohol, making water, which is an excellent leaving group. Let's take a look at the specific arrow pushing for this process. So here is our alcohol, and I'm going to abbreviate the sulfuric acid with HA. I can begin with a protonation of the alcohol, forming water. Now that I have an excellent leaving group, my nucleophile, which will be either chloride or bromide, is able to attack this primary carbon and directly displace the leaving group, as shown here. When you think about whether you expect chloride or bromide to be the stronger winning nucleophile, consider the whole set of reaction conditions and maybe think about some of the trends you've learned in lecture. Come up with a hypothesis, and you'll be able to tell if your hypothesis was correct when you analyze your data. Practically in the lab, in order to get this reaction to go, we're going to supply some heat. As we saw in the resolution of ibuprofen, when we heat organic mixtures, we tend to use a reflux condenser attached to our round bottom flask. And we'll use the same setup here with a variac controller and a heating mantle as we did in the ibuprofen lab. In order to be very prepared to set up your reaction, go ahead and fill in the table of physical constants that you'll find in the lab manual as part of your pre-lab reading. You'll determine the number of moles of the ammonium bromide, ammonium chloride, and 1-hexanol that you're using. This will allow you to identify the limiting reagent and think about how much bromide and chloride you're using relative to the alcohol. And we'll verify these numbers and discuss why we choose this stoichiometry at the start of lab. When our reaction is over, in addition to these organic products that we're so interested in, it's likely that we will have an excess of ammonium, bromide, chloride salts, and we're still going to have sulfuric acid present. These species are not compatible with the analysis we want to do on our product mixture, which will include infrared spectroscopy and which will include the use of a gas chromatography, very small column. In order to remove these salts and acids, we use a separatory funnel, which is shown here. 2 videos are going to be posted on our Sakai site of one of your Wellesley peers putting a separatory funnel into action, and I encourage you to take a look at them. When we pour our reaction mixture into the separatory funnel, which has this conical shape, and a stopcock, which can be opened and closed to allow the release of liquid, what will happen is the water solvent will form a separate layer from the organic products, which may again include unreacted starting material, as well as the bromo and chlorohexanes that you might be forming. Think about what's likely to be in that aqueous layer. Again, it's going to be residual H2SO4 and ammonium salts that we're hoping to get rid of. You'll be able to see the separation between the oil and water clearly with your naked eye, and you'll be able to drain the aqueous layer away from the organic. The organic layer is then typically washed a couple of times. The washing refers to the addition of some extra water, shaking of the separatory funnel, and allowing the two layers to settle again, and collecting the aqueous layer and adding it to our initial water collection. This allows us to remove trace amounts of acid or salts that are lingering behind in the organic layer. And it's really important to do this to be able to get a nice clean gas chromatogram. The final wash that we're going to be able to do in the lab is we're going to add sodium bicarbonate. Think about our reaction conditions and why we might want to conclude with this basic wash. After shaking with the sodium bicarbonate in the separatory funnel, you'll do one last drain of the aqueous layer, and you'll be left with a clean organic solution. The final step of preparing the product for analysis is known as drying. This is a bit of a deceptive term. We're not actually going to dry away all of the liquid so that our sample is no longer wet. We're going to instead add magnesium sulfate, which is a white powdery solid. It kind of acts as a desiccant, and it's able to absorb all of the water that's in solution. And this will get rid of any tiny water particle droplets that are remaining in your organic layer. Once you've done this, you can pour your organic oil with this white solid through a filter paper or a cotton plug using a small funnel. And this will allow you to remove those solids and hopefully get a clean organic layer that's totally free of water. So once you have this oil, we want to find out what's inside of it. So you can obtain a GCMS vial, which is a tiny glass vial. And you're only going to add a couple of drops of your sample using a pipette tip. These are going to be very small drops. Even 2 drops is usually sufficient. Our instrument is very sensitive, so we don't need a lot of material. And you're going to add 1 to 2 milliliters of methylene chloride or dichloromethane to that vial and give it to your instructor or the lab assistant. This sample will be analyzed overnight, and you will be given instructions to access your data once it's ready. The last thing you'll do before you clean up the lab is obtain an IR spectrum of your product. Think about the alcohol starting material. If you have any alcohol remaining in your product mixture, what specific peak that's very indicative of an alcohol do you expect to see in your infrared spectrum? In these last couple of slides of this week's video, we're going to take a closer look at gas chromatography mass spectrometry and look at a sample of what we can expect to see when we open up our data. So gas chromatography should remind you of something we have done in the lab before. During the second week of lab, we carried out column chromatography. And you'll remember that this was a means for separating molecules. In gas chromatography, we're also going to obtain a separation of the components of our mixture. However, instead of using solvents to force our compounds through a solid column, as we did in week 2, we're instead going to use helium as a carrier gas. And that is going to allow us to move our sample through a much smaller column. In this technique, as the name implies, our sample molecules are also in the gas phase. We vaporize them by placing them into a hot injector. Once vaporized, they'll travel through this long, thin column. And basically, the column is maintained in a heated oven to keep nice and warm. In week 2, in our column chromatography, we saw a separation that was based on polarity. In gas chromatography, our separation is going to be based on boiling point. So what we find is that the lower boiling compounds elute from the column first, and higher boiling compounds come out later. To prepare for this week's lab, you can look up the boiling points of hexanol, 1-chlorohexane, and 1-bromohexane, and predict the order of elution that you would expect if you had all 3 of these compounds present. By coupling this gas chromatography to mass spectrometry, we can gain information about the material that exits the column at different time points. So as our vapor molecules elute from the column, they enter a mass spectrometer. So you'll recall from our previous pre-lab discussions that these are basically ionized in the presence of an electron beam. And once these molecules have ionized, they are detected by a mass detector that can tell the exact mass of each individual molecule that has eluted from our gas column. So let's take a look at what the data from both the gas chromatography and the mass spectrometry portion of the experiment should look like. First, let's take a look at a gas chromatogram. You'll find on the y-axis that we're looking at relative abundance. This is basically a count, how many molecules came out at each time point. The x-axis is known as retention time. And what you'll find is that the shorter retention time is towards the left hand of the spectrum, and a higher or longer retention time is at the right. So recall that a lower boiling compound would be on this side of the chromatogram, and those that are coming out closer to 6.5 and 7 minutes will have a relatively higher boiling point. The other really useful piece of information we can gain from a gas chromatogram is the number of components present in a sample. If I count up the number of peaks that I observe, that tells me how many individual unique components I'm detecting in my sample. So on the instrument that we're using in lab, with the data analysis open software that you'll have access to even from your own dorm room, your gas chromatogram will look something like this shown here. So this is a reference GC for the starting material for the possible product 1-bromohexane. And as you would imagine, because I've used very clean reference material, I am seeing one peak right here with the X on it in my gas chromatogram. So that tells me that my sample is nice and clean. And you can see that my retention time is right here between 5.5 and 6 minutes. When you're in the data analysis software, you can get a very accurate retention time for this peak by clicking on it. In addition to being able to say at 5.5 to 6 minutes, I have material coming out of the column. So this is where molecules were eluting from that gas chromatography column. If I double click on the peak in the software, I can actually pull up the mass spectrometry data that was collected by the mass detector for all of the molecules that exited the column during that time point. And what I can see, if I bring my eye far to the right here, is what I like to call the twin peaks at 135 and 137. So you'll recall that when we have an M and an M plus 2 that are equal in height, it typically indicates the presence of a bromine atom. One caution in analyzing this week's data is that these small alkyl halides are likely to fragment in the mass spectrum. So you may not, in fact, see the intact molecular ion. You may only see masses that are smaller than what is expected. But hopefully those fragments, some of them anyway, will maintain the bromine or the chlorine atom enough that you can pick up on the unique mass signature. So caution, you're likely to see extensive fragmentation. So for instance, if you were to obtain a GCMS data for your product and it were to look exactly like this, you would be able to say with high confidence, based on matching the retention time to this reference bromohexane that I've shown you, and also by looking at the mass data and confirming the presence of a bromine, you would be able to say with high confidence that you had made 100% of the brominated product. I will also provide you in lab with a reference for 1-chlorohexane and hexanol. So your individual data may contain only one peak, or it may contain several peaks. And your goal is to identify which compounds are accounting for those peaks. The last piece of information about gas chromatography that's really important to us is that the area under each peak represents the relative quantity of the molecules making up that peak. So by comparing the area of two peaks, I can say something about the ratio of the compounds present within them. So in lab, we'll go through an example of how you can open up a gas chromatogram with multiple peaks and let the software tell you what the relative area is under each of those peaks. That will allow you to give me a pretty good quantitation of the products that are made during this reaction. So that's what we have in store for lab this week. This will be our first official organic reaction, and we look forward to seeing you.